So being able to solve sintering problems under these parameters opens up numerous opportunities. In order to understand sintering rates, it is useful to follow the analogy of fluid flow. Rates in general depend upon the gradient and depend upon the mobility, right? For instance, fluid flow in a horizontal tube, you have a rate at which the fluid is dripping out at the end of the pipe. You tilt the pipe a little bit and you can get a faster flow. So that's what the gradient does. You have a potential energy gradient in this case, and that results in kinetic energy to the material, and you have a faster flow rate. Of course, you have a low viscosity material, so it has a higher intrinsic mobility that will give you a faster flow rate. If you have a higher viscosity material, lower intrinsic mobility, you have a lower flow rate. Let's see how this translates in terms of sintering related issues. Okay. So for faster sintering, obviously, then you'll need a higher gradient and a higher mobility. So in terms of the rate, you can follow the degree of bonding, you can follow the strength as parameters. The gradient depends upon the curvature and surface area of particles, and so smaller particles will have a higher surface energy, and losing that surface energy will provide a gradient. Mobility is determined by atomic motion, ability to diffuse, and higher temperatures, smaller atom sizes help in improving the mobility. Diffusion through liquids occurs at a faster rate than diffusion across a solid, or so that also contributes towards the overall mobility. Okay, there are three typical stages that occur as you start from a loose powder, go through an initial stage where necks are formed, then an intermediate stage where there is some densification occurring and these pore shapes begin to change and pore sizes begin to become smaller, and a final stage where you can either have no porosity or some residual porosity that you can live with or that you want to engineer into the system. In terms of driving force of sintering, we've seen that the presence of a curved surface provides a stress. Right? A flat surface does not have that. Think of a balloon filled with air, right? That surface is under pressure. And another way to look at the surface is, you can see over here, two particles, and let's take a magnified region over here represented by the atoms. So the presence of the surface itself provides an energy because the top plane of atoms do not have nearest neighbors, any nearest neighbors, and so compared to the atoms in the bulk, which are surrounded by other atoms, there is an opportunity for bonding to occur with the available electrons, and so that constitutes energy. Now when you bend that plane near the surface, the distance between nearest neighbors increases further, and there are defects that are generated as well, increasing the overall surface energy that is available for minimization by formation of necks. Okay, more grain boundaries, so on and so forth. So these constitute driving forces for sintering. So atomic motion is part of the mobility that's required for sintering. Atoms can be represented by some kind of an Arrhenius type expression where the diffusion depends upon some pre-exponential or a frequency factor, and there's an activation energy related to that. And so diffusivity is typically measured in meters square per second, and it's a temperature dependent process. Okay. D naught and Q are parameters that depend upon the type of material and also the type of matrix in which diffusion occurs. A graphical plot of that equation gives you an idea of energy and the relative fraction of atoms having a known amount of energy. So at low temperature, this curve is represented by this probability function effectively, and so the area under the curve gives you the overall energy of the system. As temperature is raised, you can see that the curve shifts more to the right, and so there are a greater population of high energy atoms in this region over here. Okay, so more atoms are available with high energy that can facilitate diffusion. Okay? So what does this translate in terms of sintering? So if you follow the rate of sintering for pure iron, and you plot that rate of sintering as a function of temperature, you can see that as you raise the temperature, the rate of sintering keeps increasing. Another parameter that is important is particle size. So the Andreevsky equation is useful in following this aspect. Right. Here's fractional density plotted as a function of temperature for nickel powder that's heated at 6 C per minute. 3 different particle sizes. What are some things that you can see in this plot? For instance, at any given temperature, the smaller the particle size, the higher the fractional density that you can reach at a given temperature. Of course, if you heat something, the larger particles to a high enough temperature, you can get an equivalent density from 5 micron to as a 0.05. But in this case, you can see that you're almost gone 500 degrees extra to be able to achieve that type of density of over 0.7. Right? So basically, you need fine particle sizes and to accelerate densification. And so from this, you can see the benefits of going into the nanoscale. You can get rapid sintering, right? Assuming that you can retain purity of the powders. In terms of paths of motion overall, there are several mechanisms by which you can achieve atomic diffusion. Bulk diffusion results in movement of atoms from the core of the particle to the pore surface, and so that involves then densification. Surface diffusion can also occur and along the grain boundaries and so on, and you can also have a vapor phase transport. However, it's the diffusion from the bulk that allows densification. The other two methods, surface diffusion and vapor phase, do not contribute towards densification. The motion of these atoms contributes towards neck growth in this region and shrinkage of the pore over here in the center. If you apply external pressure, of course, you can have plastic flow as well, and you can move material from the core of the particle towards the contact region. If you follow the degree of sintering as a function of sintering temperature, like we saw for the iron particles earlier, you can see that as you get closer to the melting temperature, you can get higher and higher sintering rates. Okay. Typically, sintering is done, depending upon the material, between 0.6 to 0.8 times the melting temperature. Right? So one of the major advantages is you need lesser heat energy to sinter a material. In terms of evolution of properties as a function of sintering temperature, yes, as the density increases, properties typically tend to increase. But for a lot of materials that are very sensitive to pores, it is the elimination of pores that's going to contribute to a greater increase in properties. And this is particularly true for mechanical properties of ceramics.